Welcome everybody to my presentation about verifiable random, verifiable private random permutations in Web3. Who chose this title? It was me, I have to admit. So, yeah, this is the demo I'm going to show, the demo that I'm going to explain. But before we dive into it, maybe these are the foundational things that we solve at Integritee to reach the state to actually implement this demo. We claim that we solve confidentiality issues with our technology, scalability issues, and also interoperability issues, like talking to like Web2 services, bridges, and so on. Yeah, short outline of what I'm going to talk about today. First, what is randomness? I think it seems pretty obvious, but when you look at the details, maybe not that obvious. Then, what is a T? Because this is what Integritee is working with, and how do we use a T to build our technology stack? Then in the end, so the demo that I'm going to show you is a raffle demo, which is kind of a lottery, and that you usually you sign up online for a lottery, and in exchange for your data, you might win a prize. But how do you know that there is an actual lottery behind or not? Could be a scam. So, randomness. Randomness is a fundamental property of nature, denoting lack of pattern or predictability. However, in computers, like them being deterministic circuits, true randomness is extremely hard, perhaps even impossible. So, randomness, what does a process need to be actually random? It needs to be unpredictable. At no point in time you can make an educated guess about the next random value in the sequence. Unbiased, every output of the output set needs to be equally probable. It needs to be provable. The process how this random value is obtained needs to be, you can verify it. Tamper-proof, no one should be able to mess with the random process to reach some specific output. And non-reproducible. If you don't preserve the original sequence, you should not get the same output twice. Why is randomness important for blockchains? Obviously, when you create your private key, you want it to be perfectly random. Otherwise, there might be a slight chance that someone at the other end of the world will have the same private key and also access to your funds. But this is not what we're going to talk about. So, randomness on blockchain is mostly used to solve fairness issues in either responsibilities or rewards. In Bitcoin, for instance, proof of work is the source of randomness for block generation. In proof of stake, it is like proof of stake is the same thing for proof of stake chains. It distributes validator responsibilities. Then NFT art, we want it to be perfectly random. No one should be able to create a subjectively more beautiful NFT based on messing with the randomness. Metaverse, we want asset location to be fairly distributed. Lootbox content should be fairly distributed. And then again, more on-chain or low-level stuff, if you have a governance body, like we have it on Polkadot, and then maybe responsibilities take turns, then you also want this process to either be maybe round-robin or also fairly randomized. However, on-chain, all inputs and outputs are known. This makes random processes or random sequences eventually predictable, rerollable until a desired output occurs. There are mitigations against this, but this fact can never be completely erased. And off-chain, we have another issue. The randomness is usually opaque. Trust in a centralized provider is needed. Or if we take Chainlink for an example, which runs on Oracle, their service is just extremely, extremely expensive. And for their Ethereum randomness, to verify the randomness of the source, it costs you almost $200 US, where we say we provide it at a few cents. Last slide about randomness, about theories. We distinguish usually between true random number generators and pseudo-random number generators. The pseudo-random number generators, I think the name already hints at what is happening. It is an algorithm. It mimics true randomness. It has all of the features of randomness, like it is unbiased, it is verifiable, and so on. And however, if you preserve the input seed, which was used to kickstart the state of the random process, all outputs of the sequence are deterministic, and you can re-roll them, and it will always be the same values. Then true random number generators, they provide truly random outputs or samples mostly based on physical phenomenon like atmospheric noise or radioactive isotope decay. In CPUs, they mostly use some kind of sensors that measure something in the environment, like temperature. They are usually more expensive and therefore a bit more impractical. Now, spoiler alert, a T produces true random numbers, but what exactly is a T? This is what we are building with. So a T is or a TEE, some people pronounce it like that, is a trusted execution environment. I would say the most dominant features that we want to use when we have a T is confidentiality of data in use. So at any point in time, the user data that is inside a T is absolutely private. No one can inspect it. The system administrator cannot inspect it, and not even the operating system. It is an absolutely secure enclave. Enclave is sometimes used as like the T instance, actually. So we have confidentiality of data in usage, but we have complete transparency of what kind of computation is taking place. And we can prove what kind of computation is taking place publicly to the world. And how this usually looks like, we see on this kind of abstract slide we have. Do you see my pointer? Yes. So here we have the T. We have the open source software that is being deployed in this T, and we have the software manufacturer. And what usually happens is that when you want to prove what is running inside that T, the T will compile a so-called enclave attestation code about itself, which contains data about itself. It's like, somewhat like the hash of the binary that is deployed in the T. It contains a bit more data, like memory page allocation of the secure memory. It contains also information about the latest security patches, so that we know that when we interact with this T, not only it is an actual T, it is also safe because it has been updated. So this information is sent to the hardware manufacturer, which verifies the data and verifies that it's an actual T of this manufacturer. The manufacturer will compile a certificate signed by the manufacturer, which can then be verified. Another quite loaded slide, please for now only focus on the circle we have here, how we close the trust chain from source code to end user interaction. So hopefully we have open source code. This open source code is built, it is deployed, and the deployment can be anywhere. We don't have to trust the operator because of the T guarantees, as I explained before. Then the remote attestation is being compiled. And here is where we as Integritee come into place, the verification of this remote attestation report. And also, actually, our technology removes the need of the hardware manufacturer in this process, which means that we only have to trust in the chip design of the hardware manufacturer. Afterwards, the manufacturer is out of the game. And the difference to the original process is here that the remote attestation process is no longer censorable. So any T can always be remotely attested. And then the verification of this process is going to be on the Integritee network. So we have afterwards a public registry of all remotely attested Ts, and we know that those Ts are secure. They are, we know what kind of business logic is running, and verification of the business logic that is being deployed can be done by inspecting the open source code, which hopefully has gone through an audit, because as we all know, like, understanding code is not that easy. After this, the user can be sure that the data, like, first, all important security best practices have been employed, and also user data is only handled according to the open source business logic and not in any other way. The service provider and the system administrator have no way to actually do something with that data. So here we come back to our previous slides, where I now connect the dots. We have confidentiality, as I explained. Everything inside the T will remain inside the T. We have scalability. Might not be obvious on what I have told you before, but We provide a sidechain SDK so that you can build your own like blockchains inside the T, and because of the trust guarantees, like the individual validate tiers, as we call them, can trust each other. We have simplified consensus, which allows like sub-second block production and confirmation, and in the end up to 1 million transactions per second. Also interoperability. Like blockchains usually have issues talking to other consensus systems or other or the Web2 world, because if you do a Web2 API request, it is hard to get a deterministic result. One of the reasons why it is not possible. With a T, you can easily query the Web2 world, verify the TLS certificate of the provider. For instance, CoinGecko, if you're interested in an exchange rate, the T can verify that the TLS certificate indeed belongs to CoinGecko. If it does so, it will forward this value on chain, and then the chain only needs to know, is this T one that has been publicly verified on our chain? If yes, it will accept the value, and you have a very cheap Oracle value on chain for a few cents. Yeah, a little bit about what we do or what we have been building. We have the sidechain SDK, as I told you before. Another flavor of our SDK is the Oracle framework. We have complementary to it, a confidential computing infrastructure which simplifies deploying code inside a T, our SDK, but also other, like any kind of T. It comes with a secure Kubernetes cluster. We also provide attestation service for like Web2 companies that want to create user trust by running something in a T. They can use this attestation service, which will then forward the remote attestation on chain, and they never have to expose themselves to any crypto tokens at all, which is indeed a USP for many Web2 companies. I think, I've been going quite fast, so I can explain this slide. So this is the example of the CoinGecko Oracle. On the top, you see the T-Recal service. This first it goes through the attestation process, which will register with our pallet T-Rex, which will verify the remote attestation report and then put it into its registry. We have here our HTTP client, which runs inside the enclave directly. It establishes a TLS connection to the REST API of CoinGecko. It will fetch the value. It will do the verification, put it into our extrinsic factory inside the enclave. So the extrinsic is going to be signed by the enclave key, which has been put on chain along with the remote attestation report. Sends it to the pallet T-Recal. The pallet T-Recal will verify if it has been signed by an enclave in our pallet T-Rex. Basically, that's it. Then you have an Oracle value, which is essentially available in the whole Polkadot ecosystem. All right, so this was kind of the intro. Now, about the little demo that I'm about to show you. I call it the Integritee raffle demo. As I said, it's a lottery you can sign up with, for instance, or even airdrops. You sign up with some company that's provide you user data, then a winner will be drawn and get tokens as a reward. But how do we know? Well, with an airdrop, it is obvious because in the end, we at least have a result. It is publicly known that some value has been dropped, but we don't know if the user was actually part of the lottery or if this is even maybe some in-company account. So before I go into this, let's first clarify again those adjectives. We have verifiable private random permutations. So based on what I've told you before, can we make sure that those adjectives fit? Verifiable fits because we have this remote attestation report, which is verified by the T. So if this remote attestation report contains the hash of a business logic which performs this random permutation, we know this T can only do this and nothing else, so it has been verified. It is private because everything runs inside the T. It is not accessible to the outside. Random, well, of course, the T, as I told you, uses an SGX CPU random instruction, which provides true randomness. And permutations is just, it could be any computation that happens inside, but what we kind of wanted to showcase here in this demo, you can use potentially expensive computations inside a sidechain yeah, because we're just very efficient and scalable and cool. All right, so how does the demo flow look like? Here on the bottom left, you see what is happening. Instead of like drawing like multiple lines for all the connections, you see like which step happen on which connection essentially. So what happens first? The T will register itself along with its business logic on the integrity parachain. Then the corporation will decide to, hey, I want to create a raffle so that users can sign up for my raffle. The users will register for that raffle, and the T will store all the registered users. At some point, the corporation will tell, I mean, this can be either triggered by the corporation. It can also just be a fixed schedule, like 2 weeks, or X amount of blocks, and then the raffle registrations will close and the winners will be drawn. Yeah, so the raffle will perform the random permutation. It will forward the results to the chain. It will also forward the result, like the Merkle root of the input set to the chain, so that as a last step, the users can request a Merkle proof. A Merkle proof, I'm not sure if this is familiar to all of you, it's basically a hash tree where you hash all the input values and like 2 at a time until you end up with one value, which is the Merkle root. And if you know your own, your own key, and you can hash it, you can formulate the proof and combine your own value with the rest of the proof, which ends up at this Merkle root. And if it matches the value on chain, you know, okay, I have indeed been part of this set, even though I don't know who else has been part. There is even a slightly simpler solution to that, which might be more Web2 friendly. We can make our T stateless. It doesn't have to store the registrations of the users. They can just register with the corporation. I think the flow is exactly the same, just the way the interaction goes is a bit different. So the users sign up with the corporation, and this corporation will at some point say, hey, please draw me 2 winners out of this input set that I'm providing you, and then the raffle dApp will on the fly perform this random permutation and draw the winners. And then the cool thing is actually the users never have to talk to the T. They can just talk to the corporation and tell it, hey, please give me Merkle proof. I'm not sure if I was truly part of the set. And then they can verify the proof as before. All right. This is everything I had to say to that topic. I will now do the little demo. So what we're gonna be doing, very simple. We first launch a simple setup, which is an Integritee solo node containing the palette T-Rex, and we will also launch one of our sidechain workers. Then I'll just instantiate our CLI client with the correct values to talk to the node. We'll also see which workers have registered. Here we'll just assign the MR enclave, which we'll use afterwards for the other commands. We'll create a raffle. We will have a bunch of users register for the raffle and demonstrate how quickly this will go on, because we are a high performance raffle. We'll draw the winners, and in the end we can verify the Merkle proof. So yeah, I know we all hate CLI demos, but it's just extremely expensive to do something else. So this local setup will now start the node. Yes, it's already, I will reload to get to remove all the past values. Yeah, we already have our first block here. The T will now soon register itself, which we should see. I will tail the logs of our worker that we start up, which does not really contain a lot of important information. Hello. We just see it starts to register itself. We already see that Alice, our faucet, has funded our new freshly created T account. And then as soon as we start producing sidechain blocks, we can start with the raffle demo. This should usually happen at block 9. Is there anything relevant in the logs that we can like? Okay, see, I'm running this on my on my local WSL instance, which unfortunately Windows did not make it possible that we can access SGX, which is our T technology, through WSL. So my dev chain allows actually registering without the remote attestation report. Yes, so now we also have like the proxy account of the T on chain, which has been received some funds, and now very soon we can start. All right, so yeah, first we'll set up our CLI. This we can already do. Yes, we see our T has already been registered. This is the MR enclave, which is the hash of the T and the other security relevant data. Yes, we are producing sidechain blocks, as we can see here, and actually here we have finalized our first block. Now we can actually start. So we have the MR enclave here. I will access this to write this to our environment variable. Wonderful. So as usual, I'm always a bit nervous, as we know, even though it worked like 100 times. You don't know if it's going to work at the actual demo. So we create now our raffle. Alice is creating the raffle. It can be anybody, not only root accounts. This raffle is going to have 2 winners. We're going to see, we already see here published hash. This is a very generic event that I've implemented to just like. I didn't want to implement any more on-chain stuff for this little demo, so we just abused this generic event. The hash here is not used, but we see that we just write some data as, inside the event. We have a new raffle. The owner is being stripped because of Substrate doesn't print addresses in WASM. And we have winners count. We have 2 winners at the end. The registrations are still open. Then we will register some users for our raffle now. Let's make it a bit more fancy. We don't want 50, we want 200, so we can showcase how fast our sidechain actually is. So everything done. We should see 200 events here. Yes, we see that some user registered for our raffle with index 0, and we don't disclose who because privacy, which is what we're all about. And then the next step would be that Alice is gonna, this can only be done by the raffle creator. We want to draw winners for our raffle. Yeah, it is submitted. And then very soon we should also see the next published hash event, or actually 4 of them. I had to separate them because there was too much data. So I was very lazy and just created 4 events with different data. So we have to inspect this block here. We see that we have the first event, which says, okay, raffle index with 0, a raffle with 0 index has been closed and winners have been drawn. In the next event, we're going to see the Merkle root of all the registrations. And here we're also going to see the winner. This is just the hex encoded value of the account. So, and yeah, there's another winner down there. We don't care about this for now. So finally, our raffle user 10, this is just the seed that we have been using for like our individual users that like from 0 to 199. He wants to see, hey, have I been part of the set? And our CLI will get the proof. It will also verify the proof for us. We already see that the proof is valid, but now we have to check, have I received a proof which has actually, with a proof corresponding to a root that has actually been published on chain. And here we see, oh yes, very nice, or not so nice, I didn't win, but yeah, I was part of the input set, so I can conclude the company I've signed up with was honest and hasn't cheated me. All right, this is all I had to say. Any questions? We have like 55 seconds. Yeah.
Okay, for the verification process, you cannot distinct set on randomness from true randomness if you are inspecting, as far as I know. So what does the verification process verify?
The verification process verifies that the actual instruction that is being used inside the enclave to get the random value uses Intel SGX's true randomness source.
Okay.
Was it clear? I'm not sure.
Not so much, but maybe we can talk later about that.
Okay. Yeah.
Okay.